In this video, I'm going to talk about the angular momentum operators. So first of all, you have to take the R operator, R hat, and the P operator for linear momentum, P hat, and do a vector product, and you're going to get three components of the angular momentum, which is also a vector operator. The X component of the angular momentum is called Lx hat, and after you transform to spherical polar coordinates, including the derivative operators ddx, for example, in the linear operator for px, then you get derivatives in terms of theta and phi. Now, the thing to notice about this is that there's either a derivative with respect to theta or a derivative with respect to phi, and there's no cross terms where there's like a partial derivative with respect to both coordinates at the same time. Lz operator is going to be much simpler form. Ly looks a lot like Lx, except has some different sines and cosines and so on. So the Lz operator has a much simpler form. It's just the phi derivative times minus IH bar. So the total angular momentum operator L is usually presented as L squared. And we're going to see why we do that. It's because the angular momentum is not simply just the angular momentum quantum number little script L that you learned about in general chemistry. It's actually a different number. So if you take the L squared, Lx squared operator and the Ly squared and the Lz squared, then you can get the L squared operator, and it has this form here. And again, notice that one part has only theta derivatives, the other part only has phi derivatives. Okay, we're going to actually look at what is the effect of these operators on two of the functions that are commonly encountered in the angular momentum quantum problem. And so it's y0, 0. So the capital Y just denotes the spherical harmonic function, and the lower subscript is usually the quantum number script L, and the superscript is m sub L. And these are exactly the same two quantum numbers you learned about in general chemistry. Okay, so let's do the one that's just a constant. Okay, and this is just the normalization constant for the problem. Okay, well, we have no dependence on theta and phi, so let's see what happens when we apply Lz hat onto a constant. Well, the derivative of a constant is 0. Okay, and that's still times the original function. So we know that this is an eigenfunction of the Lz operator with an eigenvalue of 0. So the z component of the angular momentum for this spherical harmonic is 0. This is an eigenvalue relationship where this is the operator, eigenfunction, eigenvalue, and eigenfunction. Okay, and it turns out in general that the eigenvalue for the Lz operator, if this is an eigenfunction, then the eigenvalue is m sub L h bar. So if this is 0, that means m sub L is 0, which of course we already saw that m sub L, the superscript, is 0. Okay, so what that tells us is when we do the Lz, the L squared operator, we'll also get something interesting. Well, again, it's just derivatives. The derivatives of constant is 0. All right. Now, it turns out that this is going to be L, not little l squared, but it's actually little l times little l plus 1, h bar squared. Okay? And so if this is 0, that implies that L is 0, which of course we already knew when we did this. The more interesting example is going to be y1, 0, because it's not a constant. It's a function of theta, and we're going to see what happens there. So let's go ahead and apply the Lz operator to y1, 0. And so the Lz operator is going to be working on the theta function. Okay, well, Lz is just the phi derivative, and so the phi derivative of a function that has no dependence on phi, that again is just 0. And so, again, not very interesting. So this is m sub l, h bar, and m sub l is 0. Well, we can see that. Now, the more interesting thing is we're not going to get 0 for L squared applied to the function. Okay? So L squared applied to square root of 3 over 4 pi. Okay, so let's think about what we have. We have a theta function, so the theta derivatives are not going to be 0. The phi derivatives are going to be 0. So this term is going to be phi derivative of something that doesn't depend on phi. So this term will go to 0. So we'll only have to worry about the theta derivatives. So it's minus h bar squared, 1 over sine theta, d d theta, times sine theta d theta. All right, that's the operator, at least the parts that we are concerned with that aren't going to be 0. Square root 3, 4 pi cosine theta. All right, so now, this is a sequence of operations that we do. We have to do this one first. Because remember, if you have a sequence of operators, do the one that's next to the function first. So the first thing we have to do is take the theta derivative of cosine theta, and that is minus sine. Okay, and so I'm going to go ahead and put the minus sign, cancel that minus sign, and just call it h bar, squared. Write all this other operations. Okay, so now, and I'm also going to bring out the constant as well. Square root 3 over 4 pi. Okay, so now the derivative of cosine was minus sine and brought the minus out. So the next step after taking the derivative of the respect to theta of cosine theta and getting sine, now I have sine times sine, which is sine squared, right? So what's the derivative with respect to theta of sine squared theta? Well, that's going to be 2 sine theta cosine theta, right? So all right, so 1 over sine theta, and then times 2 sine theta cosine theta. All right, now finally I do this last operator, which says divide by sine theta. So sine theta cancels out, and I get 2 cosine theta. So equals to 2 h bar squared, square root of 3 over 4 pi cosine theta. All right. And the reason I did it in this particular order so that you could see, that operator function equals a constant times the same function, which is right here. And so the eigenvalue of the L squared operator is going to be 2 h bar squared. Well, if L equals 1, then that is going to be 2, because 1 times 1 plus 1, 1 plus 1 is 2, 1 times 2 is 2, that's what we got, h bar squared. Okay, so it's very nice to know some of these properties about the L squared operator. Now, in class, I'm going to ask you actually to apply the Lx operator to y10, 0, and it's actually impossible to find an eigenfunction if L equals 1 of both the L squared and the Lz and the Lx operator.